Hello, welcome back. This is Differential Equations by Dr. Oz. In this video, we're going to go through an example where we're given a non-linear differential equation with an initial condition at x equals 0. Here, the right-hand side of the differential equation is a non-linear function of y, that's sine y. In fact, we can evaluate the slopes of the tangent lines to the curve y at every point because dy over dx represents the slopes of tangent lines. So if we try to evaluate dy over dx at certain points on the xy plane, we can actually have the knowledge of slopes of the tangent lines, and we can look at the signs of the slopes. If it's positive, then y is an increasing function. If the slope is negative, y is a decreasing function. Just imagine like we have the slope or direction field provided to us. In fact, that's what we're going to do in the rest of the video. Then we can actually construct the solutions approximately, and we're going to in fact find one that is passing through the point 0 and -3 house. All right, let's get started. All right, we have dy over dx equals sine y. Before we have a good visual of the direction field by a computer software, I want you to stare at the right-hand side of the differential equation. So we have this function sine y that's independent of the independent variable x. We know that sine is 0 whenever y is an integer multiple of pi. So this n could be negative or positive, n could be 0. So these points are in fact critical points of the solution curves y. What I want to do next is to look at the sign of dy over dx, or the sign of the function sine y on the interval, let's say -5 and 5 for x, and -5 and 5 for y. So I'm essentially taking a rectangular region and looking at the sign of dy over dx. We know that dy over dx changes its sign across critical points. So now we have 4 intervals to consider for y, because the right-hand side of the differential equation only depends on y. So we take sample points from each sub-interval and we look at the function values at those sample points, and you can see that so the right-hand side function for the first interval is positive. In other words, the slope is positive. That means y is going to increase on this interval. And here, y is going to decrease, y is going to increase, and y is going to decrease on this interval. So this can tell us a lot about the direction fields that we're after. All right, now let's let the computer do the hard work for us. We would like to evaluate dy over dx on the rectangular region. So here we go. The x's are in between -5 and 5, and y's are in between -5 and 5. And what we did here is that we split the x interval into 20 equal pieces, and we did the same thing for the y interval. So essentially we have more than 400 points, and at every point we let the computer evaluate dy over dx, in other words sine y. All right, let me quickly explain what those arrows stand for. Remember that we had more than 400 points, and at every point we are looking at the slope of the tangent line. So just imagine like all of these arrows to be like mini tangent lines, and we know the slopes of those. So once you know the slope of the line, you can actually place a representative slope with an arrow that's going to tell us in fact what the direction looks like. So here, for example, it's an up arrow. That means it's a positive slope, and that means like function values are going to increase that way. And then you have slope positive, steeper positive, and on and on and on. And we can simply observe that when y equals 0, and y equals 0 here, we do have dy over dx exactly equal to 0. As you see that we have all horizontal tangent line going in this direction. Okay, and same thing, it happens at y equals pi, y equals a negative pi. And just as a representative example, here if you choose this point, the slope is increasing. So if you want to construct a solution curve, essentially what you're going to do is just to pick an initial point and sort of like follow through. So we let's say like we start here, so then the curve is going to follow this kind of like graph. So going back to our problem, we were given y at 0 equals -3/2. So this was the initial condition provided to us. Here we go, x equals 0, y equals -3/2. We are right at this point, okay? So if you follow the direction field, so as you see that arrows go in this direction, and you can go backward as well, and you can see that the arrows coming all the way from here, going all the way in this direction. So this could be like a typical approximate solution curve without even solving the differential equation. This is the best part of that. So computer does the job, just sort of like provides you the direction field, and all you do is just to pick an initial point on the region and just follow through the arrows to construct the solution, so that the solution at the end of the day looks like a continuous blue curve, as you see. If you construct another solution, let's say like if you start here, then you're going to follow through this, and eventually this is going to be the solution that you're after. All right, so I think that explains the direction field. Again, we're using the superpower of computers to come up with solution curves without solving the differential equation. That's the best part of it, because we don't know yet any solution technique to provide us the explicit or implicit form of the solution. So this is sort of like the best way to come up with an approximate solution curve. All right, this is the end of the video. Thanks for watching. I'll see you in another video. Bye.